Good afternoon, everyone. Thanks for attending this talk on a greener, cost-effective cloud with serverless WebAssembly. My name is Sohan Maheshwar. I'm a dev advocate at Fermion. We're a startup working in the WebAssembly space. I live in the Netherlands, in Amsterdam. Today's a good day. The weather's good. Netherlands is playing the Euro Championships later today. But unfortunately, I have to start with some bad news, which is climate change is very real. Some estimates actually say that the tech industry is responsible for as much carbon emissions as the aviation industry, which is sort of surprising, but really technology is at the heart of everything we do. So I think for all of us working in the field of tech, I think it's super important to think about sustainability in tech. Now, folks say that if you can't measure something, you really can't improve something. So I think step one at looking at things like carbon emissions and sustainability is not just having it as a charter in your document that you will look at the start of the year, but actually talk about it on a weekly, monthly basis. My guess here is that most people here have spoken about sustainability in their orgs, but haven't actually measured it on a daily, weekly, or monthly basis. There is a very prescribed way to look at how much carbon your software consumes. Now, the Green Software Foundation, which does a lot of work in standardizing this, has a formula, right? And they call it the Software Carbon Intensity Formula. And it's defined as C per R, where C is your carbon emissions, and R is a rate. Now, this isn't an absolute value. It is your carbon emission per something that you do. That could be per API call or per machine learning model. Now, how do you define the C? That's the more important part. So they define it as O plus M by R, where O is something called operational emissions, and M is something called an embodied emissions. Right? Essentially, you want to know when you're running a piece of software on hardware, whether it's on-premise, in the cloud, wherever, how much carbon is being consumed. The M is the embodied emissions, which means to create that piece of hardware, there has been an entire process, all the way from creating the chip to cooling it, to transporting this hardware, to destroying it at the end of the day. And your software takes a fraction of that. So that is the embodied emission. The operational emission is how much energy it takes to actually operate your software on that piece of hardware. And that can be further categorized into E into L, which is the energy consumed by the software system itself. And L is the location-based carbon intensity. For example, if you're deploying to US East 1 versus Frankfurt region in AWS, the location-based carbon intensity is very different, because how each region gets their cooling, their water, and how they operate their data centers is very different in different parts of the world. So even that matters. So you have this formula to actually calculate your software carbon intensity. Now, the Green Software Foundation recommends 3 actions you can take to improve this. Right? The third one is basically being carbon aware. I spoke about location-based intensity. So if it is not critical, you could actually shift to a region that is more carbon aware and immediately be more sustainable and consume less carbon in your cloud workloads. Today, though, we are going to talk about number 1 and 2, which is being more energy efficient, which is using electricity to perform the same function, using less electricity, or being more hardware efficient, where you use fewer physical resources to perform the same function. So everything that I say after this, look at it in the lens of being more energy efficient or hardware efficient. So as technologists, we're like, OK, fine, I got this. I'm just going to write everything to be super efficient and super fast. Done. And few of you all might have seen this image floating around on LinkedIn and other social media, where there was a study in a Portuguese university, I think a few years ago, and they looked at different programming languages itself and the energy it consumed, the time it took to compile, and the memory it consumed as well, and it was normalized. So no surprises, the lower-level languages like C, Rust, Pascal, etc. perform very well. Things like Python clearly don't. Again, problem solved. Let's rewrite everything in Rust. We're good to go. Well, unfortunately, it doesn't quite work that way in the real world. It's not just the full story with the programming languages itself. As people working in Kubernetes and cloud native, we know that very few applications actually use your whole CPU all of the time. Especially if you're in the cloud, you're using a fraction of something that's already running. In fact, this and understanding this aspect is one key towards being more carbon aware and being more sustainable, because there is something that is actually counterintuitive, which is at 100% utilization, you have 100% power of a server, but that doesn't mean at 0 utilization, it's consuming 0 power. This actually, there is a non-proportionality of this power consumed. So basically, when a server is not being utilized, it's still running, and it's using anywhere between 30 to 60% of its capacity. And this is very harmful. So in Datadog's State of Cloud report, which came out literally 2 weeks ago, earlier in June, they said that more than 80% of container spend is wasted on idling resources. If you've worked in the Kubernetes space and deploying clusters, you will know that we always design for peak workloads, which means we always end up over-provisioning, which means we always have idling resources. And this, again, is pretty harmful. If you look at this graph here, you can see that 54% of clusters are idle, 29% of workloads are idle, and only 17% is being utilized. Right? And if you look at it, that's a lot of carbon over not a lot of R. If you go back to our original formula, this is not at all efficient. So we're going to talk about being energy and hardware efficient. If you see a quick evolution of cloud compute over the years, we had the good old days of bare metal. That's definitely a joke. That wasn't the good old days. But few of you all will remember where we actually had things like server rooms running in our offices. And we moved past that to virtualization and EC2, to the world of containers, and now towards this thing called serverless. Now, serverless as a term has been around since 2012, but as a way of thinking and as a service, I would say around 2014 when AWS launched Lambda. And the way I see serverless is it's really in a state of evolution. We haven't gotten to a point where serverless is the paradigm that all of us use, and we'll talk about that. Just to context set, serverless could mean many things to many people. Right? It could mean an application. We're like, hey, I'm writing a serverless app. It's completely event-driven. It's a microservice. It's stateless, so on. It could mean a model of development as well, where I'm like, I'm a serverless dev. I don't care about writing server daemons, all of that. I'm just writing pure business logic. My platform or my hyperscaler is handling everything else. Or it could mean a function as a service. There is a function I've written. It's running there. People can use it as a service. So as context setting, when we talk about serverless, it could mean one of these things. And really, the reason serverless has gotten popular over the years is, as a dev, you can purely focus on your business logic. None of those pesky server daemons and maintenance to bother about. You can scale up and down really fast. Your hyperscalers take care of that. It's meant to be event-driven. If you have spiky workloads where suddenly there are a lot of people using you, well, no problem. You have very fine-grained isolation where one function does not influence or impact another function running in the same space. And you have an increased density as well as a better utilization of hardware, which, coming back to it, is cost and energy savings. Again, the way I see it is, with points 4 and 5, we haven't reached our peak capacity of what we can do with serverless. And that's what we will talk about. The key to understanding serverless is really understanding this concept of multi-tenancy. right? Which is how can you have multiple tenants in the same space? A crude analogy here is you have a really big house with like a couple of people staying, or that same space is used by an apartment where there are many houses. So you have many tenants in the same space. If you read the original paper written by Mark Brooker, who was on the original EC2 team, very interesting paper about the economics of multi-tenancy. Again, there is one thing that is slightly counterintuitive, which again is super interesting, which is the cost of running a system is the short-term peak traffic, the peaks of your workloads. But the value of the system is the long-term average traffic that it actually gets. So you can bring the costs closer to the value by closing that gap, which basically means if you want to get the maximum utilization of a piece of hardware, you can try and get as many tenants into that piece of hardware to bring the cost to value average closer together. We actually did some benchmarks to take a look at what this means. So essentially, we ran 2 serverless functions, and what you see there is resource usage. So you see R of A and R of B. Now, what you need to look at is you have a sum and an average. So the sum is close to 20, the line that you see on top, and the average is close to 10, and the gap ratio there is about 1.7, right? These numbers don't mean too much. It's just to highlight that there's a difference between the peak usage and the average usage. On the same piece of hardware, we added 2 more tenants, which is C and D. And of course, the peak increases, right? The peak is near 25. But the average also increases. But the gap between the peak and the average is now 1.25, which essentially, again, goes back to that point that the more tenants you can have, the more density you can have in a piece of hardware, you're actually extracting more value off of a piece of system. So this concept of multi-tenancy starts making sense when you can have very dense workloads in serverless. The current ecosystem with serverless has a couple of problems. The one big one, if you've used either Lambda or Azure Functions or Google Functions, is this concept of a cold start. So how serverless works in the hyperscalers is you have a micro VM running in the cloud. There's some code written there. And essentially, it gets an event. When it gets an event, your code has to start. It's cold, so it has to actually start. And that start takes about 250 to 500 milliseconds. How people actually work around this is they keep that instance warm, right? Quote unquote warm, by giving it a ping once in a while so that the next time it starts, it doesn't take as long to start. But even a warmed start can be about 125 milliseconds. For something that is event-driven, and in the world we live in where we need things with really low latency, this could be a problem. The other problem with serverless computing in general is everyone talks about distributed systems and microservice architectures, but in reality, you are locked into one provider when you use serverless in this way. So if you're using Lambda, you're only using Lambda. If you're using Azure Functions, you're only using Azure Functions. And even in the documentations for Lambda functions, they state that cold starts typically occur in about 1% of invocations, and they could vary from about 100 milliseconds to even up to a second, based on the programming language you've written and how you actually optimized that. People have done serverless with containers as well, and there was a stat recently in a paper by Microsoft that 81% of Azure functions are invoked once per minute or less. And these costs of keeping an application warm is not borne by your cloud provider, but by you or your customer. So in essence, you're not being cost-effective again, and you're definitely not being energy and hardware efficient. So here's where WebAssembly can actually play a big role. Anyone here has used WebAssembly? Maybe some of your liquid reply folks. Excellent. Just to, again, context set and give you a bit of history, because this part is fascinating. In about mid-2010, I think, or maybe a little earlier, a bunch of the browser companies were like, hey, how do I get Rust code or Python code running in the browser very securely. And they came up with this bytecode format called WebAssembly, and hence the name web in the name. And they designed it ground up to be performant, to be lightweight, to be secure. It has a security sandbox. So any WebAssembly module, you have to explicitly grant it permissions to access an API or a file, and vice versa. That's how it's designed. And it was designed to also be portable. So for instance, you can take a WebAssembly module, write it in any language. You can write it in Go, Python, Rust, JavaScript, whatever, and create a WebAssembly module in this bytecode format. And you can run that on your local machine, which is ARM64. You can run it on the edge running Linux. You can run it on Windows, Intel, whatever, right? As long as it's all of these, it runs on something called a WebAssembly runtime, which is again designed to be run across architectures and OSs. So WebAssembly format for the browser. The characteristics were it's performant, it's secure, it's portable, and people are like, hold on. This actually makes sense if you run it on a server as well. But for anything to run on a server, you need access to things like files, networking, system clocks. So in the late 2010s, this thing called WASI was introduced, or WebAssembly Systems Interface, which allowed you to run WebAssembly on a server with things like access to files, file systems, clocks, and networking. And you didn't need to depend on any browser API. So you could run WebAssembly on a server. And this was pretty cool, because now it opened up the doors to running WebAssembly on the server side and made serverless WebAssembly a thing. And like I said, the characteristics make it really ideal for serverless computing. It's portable. So you can swap out the underlying infrastructure, and the same code will run anywhere, right? ARM, Intel, Windows, x64, whatever. It was designed ground up to be very performant and small because of its reduced instruction set. So a Hello World Wasm application written in Rust is only 284 kilobytes as an OCI artifact. That's pretty small. Just compare that with what we have currently. All WebAssembly components sandboxed by default, and you don't have cold starts because they're meant and they're designed to be performant. If you read the paper written by the Firecracker team, Firecracker is the virtual machine monitor for things like Lambda, they defined an ideal serverless unit. Right? What would make a serverless unit ideal? And they came up with these 6 characteristics. Right? The first one, isolation, a concept of multi-tenancy. Imagine having annoying neighbors who would be in your house all the time. That's not what we want. We want one function to be able to run next to another function, and those two shouldn't be able to impact each other intentionally or otherwise. You need density. Like we said, we need to run thousands of functions, have a very dense way of running all these applications on a piece of hardware to extract maximum value. We need performance that's consistent and near-native. That's always what we're looking for when it comes to performance. We need the ability to fast switch. All of these functions or serverless units are not long-running. They get an event, they do something, and they shut down. So you need to be able to shift between different functions and clean up once a function isn't used. You need to be able to soft allocate. Suppose one function gets a lot of requests suddenly, a very spiky workload. You should be able to overcommit resources like CPU and memory so that that function can still serve its users. And of course, we need compatibility. All of us use our own custom libraries, SDKs, hosts, invariably in the real world. So you should have access to all of this. So we sort of did a benchmark between a micro VM and WebAssembly as well, and see how it would stack up and look if WebAssembly was meant for this. Just to give you an example, in terms of isolation, both are sandboxed. A micro VM is sandboxed via Firecracker and KVM, the Linux virtual machine. WebAssembly, by default, is sandboxed. That's how it was designed. The second one is interesting, overhead and density. With micro VMs, you can run about thousands per node, but look at the hardware, right? You had 48 cores, 382 GB of memory with a 3360 GB disk. But because WebAssembly is so lightweight and performant, we could do the same thing on just 8 cores, 32 GB RAM and a 100 GB disk. That is a significant difference. And again, think of being energy and hardware efficient. In terms of performance, again, both give you near-native performance, so very similar. In terms of fast switching, WebAssembly, again, outshines a micro VM that we have right now. We did say micro VMs have cold start problems between 250 to 125 milliseconds, whereas with WebAssembly, you can bring that down to less than a millisecond. In terms of soft allocation, here's the thing where with micro VM, we know this works, right? People have been doing Lambda and Azure functions at the scale in terms of high production. So you can run oversubscription ratios to as high as 10x. With WebAssembly, it's new, right? So it's untested. Hopefully, by the end of this year or the start of next year, we will start seeing these production workloads and really get benchmarks to see how much you can oversubscribe. But I can tell you, it's looking good. And in terms of compatibility, well, with micro VMs, you have Linux plus KVM only, whereas WebAssembly, you can swap out the underlying OS and architecture. It's completely agnostic, right? As long as you have a WebAssembly runtime, which is designed to run across platforms and architectures, you can run any WebAssembly module. So as you can see, it looks very promising for WebAssembly in a serverless space. I'll show you a quick demo of an open source tool called Spin. Spin is completely open source. We recently hit 5K stars on GitHub. We all know that that's the only metric that really matters. We have 75+ contributors. It's open source. Feel free to contribute. I'm going to show you a quick demo of just creating a simple hello world using Spin. Just a simple 2-minute demo, nothing extremely production ready and stuff. I have the Spin SDK and CLI installed. Sorry, it's the Spin CLI installed. I'm just going to do Spin new. And you can see on the left are the different types of triggers. Remember, in serverless, you need an event. So an event could be a cron job. It could be HTTP, the most popular, or even a Redis pub sub message. Right? So let's choose HTTP. On the right, you'll see a bunch of different languages. I hear all the cool kids are doing Rust, so I'm going to say Rust. And we'll call it KCD Munich. Description. And you can specify different paths to run a WebAssembly module. Right? So right now, I can give it my default. So any ping, any request to this WebAssembly module will run this Rust code. But I can say /admin and actually have another module written in Python, and it would still work, because we're all compiling to WebAssembly. So I'm just going to give this, and I will say KC. And I will open this. Just a couple of things you need to know here. This has something called an application manifest, which is a TOML file. That's right here. Maybe I'll increase the text size for the folks at the back. And you can see the different triggers right here. Right? You can have multiple triggers in the same app. On line number 9, you see trigger.http, a route, which is the default route, which triggers a component called KCDM. And on line 13 onwards, you'll see all the details about that component, including line 15, which says allowed outbound hosts. If I have to make a HTTP call, I have to explicitly specify the URL of that call because of the default sandbox of WebAssembly. If I have to access a file, I have to write it in my spin.toml, or else nothing can access this WebAssembly. So that's the default security sandbox. And my source file is fairly straightforward. I'm just going to say hello KCD. All right. I'm going to explain this very simply. You don't need to know Rust or anything else. All you need to know is line 6. It's a simple request response model. So there's a request coming in, and we are in line number 8, creating a body to send a request out. And typically, you would do some coding, or you would do some operations in between. Oh, sorry. So all I'm going to do is just say spin build, And this is the first time it's building, so it'll fetch crates, etc. Usually, the builds after this are much quicker. And I can actually set this up and running locally as well to do local dev testing by just saying spin up. Right? And we have it running on localhost. So I'm just going to do a curl request to this right here. Yeah, there we go. I'll just do this, and we see a hello KCD. Right? Again, just a simple hello world type program. What I actually want to show you is this. There is cdsrc. Oh. I want to show you the Wasm file itself. This is, oh, sorry, I'm going to do this. My tab button has stopped working of all the things that could go wrong. CD. My apologies, yeah. My apologies there. OK, I do ls. Yeah. Yeah, oh. It's hidden way below. There we go. So you can see the Wasm file. It is a very small, less than 2 MB file. That Wasm file itself is the bytecode that isn't human readable, but this is what it looks like. So again, we don't really need to care about this. None of us can really read this. But what you need to know is the WebAssembly runtime can read this. This is the bytecode format. All right. How do I shift screens here? Yeah. In KubeCon this year, we, along with Liquid Reply, any Liquid Reply folks here, and SUSE and Microsoft, launched this open source project called SpinCube. Essentially, SpinCube is your way to put WebAssembly modules into Kubernetes. Right? It is part of the CNCF sandbox. Again, fully open source, so feel free to check it out. This is not a SpinCube talk, but there are different aspects to SpinCube. On top is the development of a Spin app or a WebAssembly app, which you can scaffold with, and get a YAML file. When you do a kubectl apply, essentially there's a custom resource definition that's created. And we have a runtime class manager, which allows us to run WebAssembly modules in a Kubernetes cluster. Right? Do check out SpinCube. The interesting thing was, again, literally last week, we were able to hit 500,000 WebAssembly serverless function invocations per second. Right? I'm just going to let that number sink in. 500,000 Wasm serverless functions per second on a 6-node Kubernetes cluster. Right? And the only sort of bottlenecks we had were the networking bottlenecks in the hyperscaler. So that number can be pushed beyond as well, is what we're thinking. This load was be able to sustain over a period of time, too. So in terms of how much it can scale and in production workloads at peak, again, it is looking good, so do check it out. The last thing I want to just quickly tell you about is the component model. Right? This will be the future of WebAssembly and maybe software development, where, say you have a JavaScript app which needs a YAML parser and a date formatter. You can actually implement a Rust YAML parser and a Python date formatter in the same app using WebAssembly components. So you have a component that exports something. You have another component that imports something. You can actually join those two components if they're written in different languages as well, creating a new component. And this is live right now. You can check it out. It's very interesting. And this changes how we think about builds and CI/CD. Because CI/CD today, as you can see in this YAML file here, you're bundling a bunch of Go versions. You have different test environments where you have OSs, architectures. You're packaging for different versions. This is from the Docker file itself, Docker's documentation itself. And look at line number 2. You're packaging for different platforms. This is neither energy or hardware efficient. But in a componentized ecosystem, you can go from multiple builds, OSs, and architecture into one build, which is like your WebAssembly Wasm preview 2, as it's called, one test, which is your WebAssembly runtime, and different components which are already packaged. I don't even need to run benchmarks to tell you this is more energy and hardware efficient. Anyway, I hope you learned something new today. I think the key takeaway is to start the conversation about sustainability in tech at your companies, at your local meetups, or wherever, because I think it's high time we need to. I can take questions off stage because I'm out of time, but feel free to connect with me on LinkedIn as well, and I'd love to hear from you. Thank you.